In this video, we're going to discuss our next reaction, and this is our first reaction, I guess, of haloalkanes. So haloalkanes, we talked about their general classes of reactivity, the types of things they like to undergo. We started by saying they like to do substitution reactions and elimination reactions, and those are really the big two. Within each of those broad classes of reactions, there are kind of a few broad variants, I guess, of substitution and elimination. So what I want to do is start with the first substitution reaction that I want to learn, and that is the SN2 reaction. So this is really one of the most important reactions that we're going to talk about in this class. And so SN2. So you can kind of think about the N as being subscript, and then the S and the 2 are normal sort of typeface, and this is the SN2 reaction. So all of these reactions that we're going to talk about have a name, and the name is important to know. And so S, that is substitution. Substitution, so this is of those two types, elimination and substitution. This is certainly a substitution one. The subscript N, that means it really directly means nucleophilic, or by a nucleophile, and we'll talk about what that is in just a second. And then 2 means we have a bimolecular reaction. That is to say, when we say a bimolecular reaction, there are two reactants, I think I just want to say, in the rate determining step, or involved in the rate determining step of the reaction. Okay, now what this looks like is we generally take some haloalkane, and I'm going to draw the haloalkane like this. So a haloalkane, if you recall, is a series of carbon and hydrogen atoms with at least one halogen attached to the carbon, and there's only sigma bonds present in the molecule. So R, this corresponds to kind of an alkyl/alkane molecule. And then X is our usual halogen. For the most part, it's going to be bromine, but we'll see examples where iodine can work. We can get iodine to work. Sometimes we can even get chlorine to work. Fluorine really never works, but I guess if you put the X is equal to fluorine, then it certainly would be a haloalkane still. It just doesn't do this chemistry that well, this transformation. And we're going to let that react with a nuc minus. So nuc minus, I think we discussed in a previous lecture. This is our nucleophile. And the nucleophile has, it sort of provides or donates electrons / lone pairs. So if it's going to give its electrons, it usually gives those in the form of some lone pairs. I think that's a good way of thinking about it. And then lastly, it doesn't have to, but it often has a negative charge. So I guess this whole thing, this whole thing requires brackets. So we're going to let those two react. And then what we get is R binds to the nucleophile and X leaves as an X minus. And so just to recall, the formal charge on X is going to be -1. It's picked up a lone pair of electrons that were once part of the R to X covalent bond. But now with that additional lone pair, its formal charge on X, if it's a halogen, it's group 7, -0 bonds, -8 electrons. That's a -1 charge. Now we formed a new bond between R and our nucleophile. Now the thing to recognize is that X serves as the leaving group. So X, our halogen, is a leaving group. And we said that last time, that it's either pushed off or it's either kind of pushed off or swapped off. It kind of, yeah, or just kind of falls off. But either way, the X in most of the chemistry we're going to be talking about, I think all the chemistry we're going to be talking about related to haloalkanes, the X sort of falls off. Okay, so let's look at a specific example to digest this in more detail, because this has only got variables. So a specific example for the SN2 reaction would be, what if we took bromoethane and reacted it with NaOCH3, and then over the reaction arrow, we're actually going to write the molecule shown here, which is acetone. And then to the right of the arrow, to the product side of the arrow, we form this molecule plus NABR. Now, what I think I need to do is I need to go onto another page of notes. So hopefully you don't have to turn the page, but I'm going to be referring to this. So I think it makes sense to copy this. Okay, I'm just kind of giving you all a chance to catch up. Well, I guess you know, what else am I going to do on this page? First thing I'm going to do over here is paste this. Okay, anyway, sorry about that. Okay, so we have this reaction. This is our specific SN2 reaction that I provided on the previous page of notes. I'm going to label the components here as A, B, C, D, and E. Now let's break them down. So A is often called the substrate / electrophile. The substrate / the electrophile. And for SN2, this is always the haloalkane. So for the SN2 reaction, this is always our haloalkane. Now, I've just defined a new term, and that's the electrophile. It sort of sounds like a nucleophile, and that's good. Those two things are paired. So the electrophile. And when I say this is an important term in organic chemistry, in chemistry as a whole, that's a huge understatement. This is something that if you want to keep going in chemistry and any form of chemistry, whether it's organic or biochemistry, or let's put it this way, if you want to do anything in molecular science, including biology, big way biology, that's why I'm phrasing it that way, you need to know what electrophiles and nucleophiles are. So the electrophile is the molecule with affinity for electrons. Now, electrons correspond to lone pairs, which corresponds to, in many cases, but not always, negative charge. So the electrophile has affinity, or if you hear the word phile, that could be interpreted as loving / affinity. It just, if you've got this phile suffix, you have some affinity for whatever is in front of the word. So in this case, it's electro affinity, electron affinity. Electrons come from, in our case, molecules with lone pairs. Lone pairs, an excess of lone pairs often leads to a negative charge or a negative formal charge. Okay, so the electrophile is the molecule that has affinity for electrons. And I'm saying that's the haloalkane. The haloalkane is our electrophile. Now that's in contrast to B, which was the NaOCH3. I'll write that again down here so you can see it. And the electrophile was, I'm going to write that as Rx. And then A is this. So I'm just kind of rewriting some of this stuff. Okay, so NaOCH3, this is our nucleophile. Okay, the nucleophile, once again, we have that phile suffix. So the nucleophile is nucleus loving. Nucleus loving. I'm going to define nucleophile broadly down here in just a second, but let's say, what is B? B is something that has lone pairs / electrons and possibly a negative charge. So the nucleophile is nucleus loving or has affinity for nucleus. This is the thing that's attracted to positive charges. Now, those positive charges could be partial charges or full-blown charges. It's attracted to the partially positive charges. Now, the nucleophile, in some respects, looks a lot like a Bronsted base. That is attracted to H+. And often, but not always, often nucleophiles are also basic. That is, if we're going to design some sort of molecule that has an affinity for positive charge, then it could be attracted to an H+. So nucleus loving, recall that in the case of the nucleus only has protons and neutrons, and really it stores all positive charge. So the positive charge of an element, of an atom, is in the nucleus of the atom, right? So that's just where we put the protons and neutrons. So any charge that's in the nucleus is going to be positive. We don't have elements that exist without protons. So positive charge is in the nucleus. So the thing that has affinity, loves the positive charge, is going to be the nucleophile. It loves the nucleus. Whereas the thing that wants the electrons is the electrophile, or the thing with affinity towards electrons. And, maybe we could have called it a protophile instead of a nucleophile, but that's just kind of what chemists called it, was nucleophiles. Okay, now we haven't defined what C, D, and E are yet. They're not really a big deal, but let's just take a second to reflect on the fact that the vast majority of organic reactions involve nucleophiles adding to electrophiles. Okay, that is a critical point. So understanding the vast majority of organic reactions involve, okay, I said that right. That's just a really important point. That's something that is not just important for this test or this class. This is something that if you want to be a molecular scientist, you should, this should be like on the forefront of your mind as you're crossing the podium to accept your degree, whether you're a molecular scientist in the chemical realm or the physics realm or the chemistry realm, physics realm or biology discipline, any of those disciplines or realms, okay? You have to know that the majority of covalent bond forming events in the universe involve protons adding to, nucleophiles adding to electrophiles, okay? And we'll, where we would see maybe a difference is with radical reactions. So free radical reactions don't necessarily follow this, although you could classify some free radicals as being electrophiles and nucleophiles. So it still kind of holds. But anyway, that's just a really important aside. The majority of reactions in the universe involve nucleophiles and electrophiles combining with each other. Even an acid-base reaction is kind of a nucleophile, the base, adding to the electrophile, which is the acid. So acid-base reactions are also consistent where we have the base, which has the negative charge, which has the lone pair of electrons, engages the acid, which provides the H plus in most cases, which provides or supplies the positive charge for the nucleophile to have affinity for. So the base is our nucleophile that's attacking the acid, which is the electrophile. Okay, so know this stuff. It's important. Okay, now what's C? C, if you recall, was when I put this molecule over the arrow. So C was this molecule. This is the solvent for the reaction. This is an experimental detail. That is to say, it doesn't sort of directly tell us what types of things are going to be formed as a result of the reaction, but it's a nice detail to know if you were going to actually go in the lab and set up this experiment, you would want to add a solvent. An appropriate choice of solvent is critical for the success of a reaction. And so this is sort of a non-stoichiometric additive. And so it's placed over the reaction arrow. Like you wouldn't necessarily do too much in the way of stoichiometry if you're actually figuring out how to set up or perform the SN2 reaction we laid out. You would want some ballpark figure as to how much acetone that you should add, and maybe you want to be extremely precise in some circumstances, but it doesn't contribute directly to which bonds are broken and formed. So we don't put it to the left or the right of the arrow. It's not really a starting material. It's not really a product. It's just something that helps facilitate the reaction, so it goes over the arrow. Things that facilitate a reaction are often drawn above or below the reaction arrow. So you might see something like A gives rise to B, and then over the arrow we might put solvent, temperature, even below, just to make it look more aesthetically pleasing, we might put it below so that there's like some symmetry. We could have time and then percent yield. Maybe anything that might be relevant to making sure that the reaction is successful, but doesn't necessarily directly tell us what bonds are being broken and formed. We would put those above or below the arrow. It's not something to worry about too much. It's not something to really strictly adhere to. What I want you to do is just get comfortable. If you see stuff drawn above or below the arrow, don't freak out. It really doesn't mean too much. We maybe could have put things to the left and right of the arrow. It starts to get to be a really long line when on the left, we want that to be starting materials. On the right, we want that to be products. So anyway, nothing too strict though to worry about. It's not like IUPAC is going to come down our necks if we put it above the arrow when it should have been below the arrow. There's nothing like that. Okay. Now, the next two things in the reaction that we put in our notes previously, D, so D was this thing, and it was to the right of the arrow. I like to call this the organic / desired product. So it's a product of the reaction. It's the product that we often care about. So what we care about are strong words. Do we not care about the other thing? No, that's not always true. It's just that in organic chemistry, we're typically studying carbon molecules that predominantly have the element carbon in them, and then transformations of those carbon elements. As a result of doing many reactions with carbon, we're going to see some byproducts form, and that'll get us into the last entry, E. We'll see these byproducts form, and they're just something else that comes along for the ride that must be produced because we cannot create or destroy matter, but it's nothing that we really stress out about. Like if we don't totally understand excuse me, if we forget to like isolate or characterize or measure the amount of byproduct that's formed, it doesn't really, it's okay, because we really cared about making the other thing, the thing with the carbon atoms. So this is, E is going to be our salt byproduct. And I should have led with what this was. So we had NaBr. And if you look, NaBr looks a lot like sodium chloride. It's table salt, which is NaCl. And that's no coincidence. I mean, Br is a halogen. It will serve as this way. But this is the combination of the counterion for our nucleophile and the leaving group, really the halogen leaving group. So the counterion for the nucleophile was Na+, and the leaving group was Br-. So when bromine left, it left as Br-, and the counterion, Na+, we'll get to in another lecture. That's just that's just something that we need to do to balance the charge. I mean, maybe it's worth, we can talk about it sooner rather than later, but let's kind of, what I want to do is look at another example of this. Let's say we have, here, let's do a cool example. Let's take CH3Br plus KCN in DMF. And if we do that reaction, we'll get, let's go ahead and draw a bond line structure. These two molecules. Okay, now let's label everything. So we want to label the nucleophile, the electrophile, the product, the solvent, and the byproduct. Okay, so the electrophile is the haloalkane, so that's Rx, and that's going to be the CH3Br. The product, this is going to have the C atoms, and it's on the right side of the equation, so that's going to go right here. The solvent is going to be the thing above the arrow. And the solvent is often sort of maybe the thing that we're less familiar with, but all we're doing is just providing a detail so that we give ourselves a chance to be productive with the experiment. So the solvent is above the arrow. Now the byproduct, this is going to be a salt. Now let's see, did I get everything? Oh, I forgot the nucleophile. So the nucleophile, this is going to generally, it reacts with the electrophile, and it's often negative and has a positive counterion. Now let's see, what color did I not use? Looks like purple. So the nucleophile in this case is KCN. Okay, so that's us practicing looking at these reactions and trying to label each of the components of the reaction. I think that's a helpful way to start learning about SN2 reactions. We'll talk about the SN2 reactions in more detail in upcoming lectures. I think it might be healthy to take a second to talk about counterions in organic chemistry before we move on to more discussion of the SN2 reaction.